Until now, we have studied the behavior and the biasing and the design of single stages. You are still working on an amplifier, on antenna, the active antenna, in which you build the amplifier with separate stages. So either feedback stages or non-feedback stages, balance stages, all kinds of stages that we have discussed. Today, we will discuss the design of the active antenna, but let's say it's only an example, the design of amplifiers with overall feedback. So we are going to discuss the design of the feedback configuration and the controller, design considerations for the controller of negative feedback amplifiers. We will start with the design of active antenna configurations. Basically, this is a recap of the uh, previous course. So you find a lot of links to the homologation program that discuss all the topics um, discussed here in this presentation. Also, the next presentation about controller is, let's say, an integrating topic. It integrates basically all the knowledge we have done until now. So both the knowledge from the previous course, the third year course, and the knowledge from this course. So we are going to put everything together today. First, we start with the design of active antenna configurations. So, a little recap. We have modeled amplifiers with the aid of two ports, and we would like to describe them with our transmission one parameters, as we have discussed in the previous course, but also already in this course. If we do so, we can write, for example, the input impedance as a function of the transmission one matrix parameters A, B, C, D, and the load impedance. The importance of this is that we can find from this values to design for A, B, C, and D. So it is not the intention to calculate it in this way, but this expression gives us information about how to design. Let's also consider the output impedance of a two-port if it is driven from a source. So then the output impedance can be written also as a function of the transmission one parameters, and then of course as a function of the driving impedance. So if we have requirements for both the input and the output impedance, we can try to find values for A, B, C, and D. For example, if we want to have zero input impedance, we know that A and B should be zero. And C and D should be, one of them at least, should be non-zero. If we want infinite input impedance, then C and D should be zero, and one A or B should not equal zero. So the design of negative feedback amplifiers we have studied in the previous course tells us that we can design these parameters A, B, C, and D. Each parameter can be set with the aid of a feedback loop. So if we want to set 4 parameters to an accurately defined value, then we create an amplifier with 4 feedback loops. So how to do this? This has already been discussed in this course. That's why I show you this slide immediately. It was a slide that was shown to you when we were discussing the local feedback stages. So with series and parallel feedback, we can fix parameters or set parameters of the transmission one matrix, A, B, C, or D, to certain values. For example, if we want to set A to a certain value, we need to have series comparison at the input. So I hope you remember this, otherwise you go back to the previous presentation. Let's see what this means for our active antenna. So the input impedance of the active antenna can be either infinity or zero. Why? You would say the voltage is what we want to know. Yes, definitely. Voltage is the information carrying quantity at the input of the antenna. but the antenna impedance is accurately known and can be used as VI converter. It doesn't add any uncertainty, and there is a unique correspondence between the current and the voltage delivered by the antenna. So we can have input impedance 0 if we want to sense the current, and we can have input impedance infinity if we want to sense the open circuit voltage of the antenna. The output impedance of the antenna should be 50 ohm. That is because it should drive the cable with 50 ohm. And we can use for this, of course, feedback techniques, but also brute force techniques. Let's say just connect 50 ohm in series or in parallel with an amplifier, as has already been discussed in the design of the CS stage for the output. So the required transmission 1 parameters now follow from the expressions for the input impedance. So either you select 0 or infinity, the output impedance, and that will give you ratios of values. It will not give the final value of A, B, C, and D. And the sort of to load transfer, that's the final one you need to set the value. And for voltage from the antenna, so Vs is the antenna voltage and VL is the load voltage across the load impedance, which is 50 ohm, you can write down this expression. Again, this expression is not intended to be used for calculating of the values. It's more for design parameters, setting the design parameters A, B, C, or D. It's not for calculating the transfer. No, it's a design equation. So we have a few amplifier configurations invented for you already with negative feedback, and we want to check if you are still familiar with the concept of sensing in series and in parallel, and comparison in series and in parallel. So we've shown you some configuration here, and we would like to ask you which parameters have been set by negative feedback. Okay, the correct answer is both A and B have been set by negative feedback. Let's see how it works. The resistor in series with the output converts the current that is delivered to the load into a voltage, which is transformed by the transformers and placed in series with the input. So we have series feedback at the output and series feedback at the input, which fixes parameter B. The other transformer, the lower one, senses the output voltage, the voltage across the cable, and places a copy of it also in series with the input. So this one is parallel sensing at the output and series comparison at the input. It is voltage to voltage, which means it defines parameter A. Parameters C and D are both 0 because C is the trans impedance gain of the amplifier, which means you are going to put a current in and see what will be the voltage out. But if you try to put a current in this amplifier, it cannot be allowed because there is a annullator at the input, so the input voltage will immediately rise to infinity, which makes C 0. Similar can be said about D. So C and D are both 0 and A and B are set by feedback. And if we now go back to our expression, then you see that A and B are set by feedback, C and D are 0. So the output impedance is B over A. And by knowing A and B, we also know, and since ZL is the output impedance, so we also know the voltage transfer and can calculate from that A. And then we know B. That's the way, the sequence of designing it. We have another one, maybe one more poll, because I have 5 configurations, not only, and we're not going to poll them all, but this is the second configuration. Now, maybe it is tempting to say A and B, but in this case, only A is set by negative feedback. You can see we have a transformer placed, of which one winding is placed in parallel with the output of the amplifier. So it senses the output voltage of the amplifier and places a copy in series with the input. That is one feedback loop, and it only fixes parameter A. So it sets parameter A to 1 over the transformer ratio if you go from secondary to primary, to output of the amplifier to the input. Div B of the amplifier is definitely set because the output impedance is set by the resistor added in series with the output of the amplifier. But this is a brute force technique because at the output of the narrator, the output of the nullarator, you will find 0 ohm because we have parallel feedback there. So we have 0 ohm at the output of the amplifier, and then we place a resistor, and in this case 50 ohm in series with it, to create an output impedance of 50 ohm. So indeed, B and A of the amplifier will be fixed, but only A will be set by means of negative feedback. So we have other configurations, and maybe you can study them if you read again these slides, because the poll is still on the slide, but we are not going to do the poll again, because otherwise we're polling all the afternoon. So here, the transformer is replaced with a passive feedback network, in this case, a capacitive divider. So basically it does the same. Instead of having non-energetic feedback, we have passive feedback. And here we did another configuration. Here we sense the short circuit current. We have parallel feedback at the input, and then we sense again the current to the load, transform it into a voltage with a resistor, make a copy of this voltage and differentiate it again so that we can fix the output impedance. This is a nice thing to study for yourself. If you're not familiar with dual loop feedback, this is a nice study. So then we have a last one, which is here just sensing the current of the antenna, making a trans impedance amplifier, which is now integrating because as in the previous case, because the antenna voltage to current is differentiating, so then integrating, then we have an instantaneous transfer again, and then we just make a brute force output impedance again by placing a resistor in series with the amplifier. This is for the people who did the antenna amplifier in the third year. This is the structure that we have chosen in the previous course. The reason for this was that there is no input voltage swing at the input of the antenna, which makes it easy to apply electrostatic discharge component there to protect the input from electrostatic discharge. And those elements often have a nonlinear QV characteristic, so you can say nonlinear capacitance, and in case of voltage you would have voltage swing across them and you would have distortion, but in this case there will be no contribution of distortion of such elements. In this course we will again focus on this structure that we are going to design in more detail, but of course you are free, if you want to do design yourself, to select any other configuration. So there are more. This was only a few. We didn't do amplifiers with current output and then shunting the output. So I invite you to invent more configurations yourself.